Problem number 9. We are asked to compute the double integral over S of f dot n d sigma for this vector field f. And what is S? S is a portion of the cylinder given here. So we want to parameterize our surface here. And this is the parameterization that we want. So R of theta comma z is, this is a cylinder of radius 3. So 3 cosine theta, 3 sine theta, and z. And z runs from -3 to 3. Theta runs from 0 to 2 pi. I have to be careful here. X and Y are both positive. So in the xy plane, it's only this chunk here. That's not theta runs from 0 to 2 pi. That's theta runs from 0 to pi over 2. We'll also need the cross product here, r theta cross rz. And so we end up with 3 cosine theta, 3 sine theta, and 0. Okay, so what's going on here? F of r of theta and z. Let's plug in our parameterization into the vector field. Y is 3 sine theta. X is 3 cosine theta. E to the x times z, e to the 3z cosine theta. Okay, now we need f dot product with this cross product here. And what do we get here? 3 sine theta times 3 cosine theta is 9 sine theta cosine theta. Plus 3 cosine theta times 3 sine theta. Okay, another 9 sine theta cosine theta. Plus 0 times this. Okay, that's 0. So 18 sine theta cosine theta. So we are going to integrate. Theta runs from 0 to 2, nope, not 2 pi, pi over 2. Z runs from -3 to 3. There's not, I almost wrote R there. This isn't integrating in cylindrical coordinates like a triple integral. It's just a double integral here. 18 sine theta cosine theta dz d theta. And so this will be a very straightforward integral to evaluate with a substituting in u is sine theta, du is cosine theta, d theta. Okay, that's problem number 9. Problem number 10 here is another flux integral. What's going on here? We have portion of a sphere here with z is greater than or equal to 0 with one little catch, oriented with the inward pointing normal vector. Oriented with the inward pointing normal vector. Okay, so we need to write down our parameterization here. And so, okay, r is 2 here because, x squared plus y squared plus z squared is equal to 2 squared here. 2 cosine theta sine phi. 2 sine theta sine phi, 2 cosine phi. And now we have to be careful. Now we have to be careful about the direction here where it says that we want inward pointing normal vector. Okay, so I just copy this down here. R squared is 4 sine phi cosine theta sine phi, sine theta sine phi, cosine phi. I just copy this down. This is an outward pointing normal vector. how do we patch this up to make this pointing inward? We slap a negative sign on it. Okay. And so at this point then, everything else goes through in a straightforward fashion. F of r of phi theta is going to be 0, 0, x squared plus y squared. So x squared is 4 cosine squared theta sine squared phi. Y squared is 4 sine squared theta sine squared phi. Note that we can factor out, 4 sine squared phi from these two terms, and then we'd have cosine squared theta plus sine squared theta. So we're just left with 4 sine squared phi here. F dot product with the cross product of the partial derivatives here will give us 0 times this plus 0 times this. I guess I should write down the negative 4 sine phi here times cosine phi times this. Okay, so negative 16 sine cubed phi cosine phi. Okay, so this is what we are integrating. So we are going to integrate, so one full loop around the circle, theta runs from 0 to 2 pi, and then phi runs from 0 to pi over 2. So negative 16 times sine cubed phi cosine phi d phi d theta. And the appropriate substitution to do here would be u is equal to sine phi, du is equal to cosine phi d phi. You can use that to evaluate the rest of this.